Just a moment. Okay, it's on now. Okay, can we start now? Yeah. Hello, everyone. I am Edi Baskoro. Good afternoon, good morning, and probably good evening to all of you from various time zones. Welcome again to our Combinatorics today's series, and we are very happy to see you again in the second year of this series. We would like to extend our gratitude to the Dean of the Faculty of Mathematics and Natural Sciences, Institut Teknologi Bandung, Professor Wahyu Sri Gutomo, for the constant support to this event. And in fact, he's always able to allocate his valuable time to attend and to give a welcoming speech in this event. And of course, our big welcome to our today's speaker for this event, Professor Nobuaki Obata, one of the productive and best combinatorists from Tohoku University, Japan. Konnichiwa, Obata Sensei.
Konnichiwa, Baskoro Sensei.
It's been a long time not having met each other, right? And hope you are well in Sendai. And I would like to mention that Professor Obata has been visiting ITB for many years, many times, yeah. And we have been having fruitful collaborations with him, and also, of course, with Tohoku University for joint research, joint publication, as well as for student exchange, particularly for doctoral students. And Professor Obata has become our distinguished member of our Combinatorial Mathematics Research Group at ITB, and hope we can continue with more productive collaborations. And in this occasion, I also would like to welcome all colleagues, friends, and students attending this program. We are very happy to have you here. This program, organized by the Combinatorial Mathematics Research Group, Faculty of Mathematics and Natural Sciences, Institut Teknologi Bandung. And this year, we will have 14 speakers for this series. And all the speakers are outstanding combinatorists from various countries. And now we are all very excited and honored to have Professor Nobuaki Obata from Tohoku University, Japan. He will deliver a lecture with the title Quadratic Embedding Constants of Graf, and will be chaired by Dr. Hilda Asiaton. Before I give the control to Dr. Hilda, I would like to invite the Dean of the Faculty of Mathematics, Natural Sciences, Professor Wahyu Sri Gutomo, to give a welcoming speech. Professor Wahyu, time is yours. Yeah.
Thank you, Prof. Edi. Okay, everyone, it will be short. First of all, I would like to express my sincere gratitude to all of you for being able to keep this schedule on track. Combinatorics Today series in 2022. And this is the second Combinatorics Today series, I think, in this year.
Yeah.
And especially, I would like to thank Prof. Edi and Combinatorial Mathematics Group for accompanying and making sure that this event will that this event can be held accordingly. And today we have our special guest, our special lecturer, Professor Nobuaki Obata from Tohoku University, Japan. And of course, many thanks to Professor Obata. And I hope that this meeting, this lecture will broaden our interest and comprehension on the combinatorial mathematics, and also can be a fruitful bridge for our young researchers and students, and to grasp and also to share ideas, and also to have a moment or a medium for a discussion. And once again, I would like to thanks all of you, all the participants, for maintaining this event, and also for participating in today's series. So without further ado, I would like to once again thanks to Sensei Obata, and from our on behalf of the faculty, I would like to say arigato gozaimasu. Thank you, Pak Edi and Obata Sensei. Time is yours. Thank you very much.
Okay, okay. Thank you, Professor Wahyu. And now, before we go further, let us have a photo together. Yeah, for remembering. Pak Yusuf, please help us to have a photo together. Yeah.
Okay, for our participants, please open your camera. This photo session will only include participants who open their camera. So I think I'm gonna wait around 30 seconds for those who want to open their camera.
Yeah.
Okay, so there's only 40 participants, so I should be able to take our photo in one screenshot.
Twice. 2 pages.
Actually, I can do it once. The maximum is 49.
Oh, okay, good.
Okay, so I'm gonna take the screenshot now. So please prepare yourself. 1, 2, 3. Yeah, thank you.
Okay, thank you, Pak Yusuf. And now I ask Dr. Hilda, please chair the session. Yeah, the session. Thank you.
Yes. Thank you, Pak Edi. Good afternoon and good evening, everyone. It is nice to meet you again in the Combinatorics Today series. It is a great pleasure for me to be the moderator for our speaker, Professor Nobuaki Obata from the Graduate School of Information Sciences, Tohoku University, Japan. His talk title is Quadratic Embedding Constants of Graphs and Related Topics. Before we proceed, allow me to share with you the summary of Professor Obata's curriculum vitae. Yes. Obata Sensei obtained his bachelor and master degrees from Kyoto University and his PhD from Nagoya University. After completing his master degree, he started working as a lecturer in Nagoya University. After finishing his PhD, Obata Sensei had opportunity to do research at Mathematics Institute, University of Tübingen, Germany for 2 years. And in 2001, Obata Sensei was promoted to a full professor and moved to Tohoku University. Obata Sensei was involved in administrative tasks. He served as the Dean of Graduate School of Information Sciences for a year and as a Vice Dean for 6 years. Since 2008, he has been in charge as the editor of, as the editor-in-chief of Interdisciplinary Information Sciences, an international journal published by GSIS Tohoku University. And he also a member of editorial boards of some international journals. His publication records are quite impressive. Obata Sensei has published more than 80 papers in journals and more than 110 papers in conference proceedings and book chapters. He has written 3 books in English and 8 books in Japanese and has edited at least 15 books. These are the covers of the 3 books in English, but unfortunately I couldn't find the books in Japanese. Now for research interests, I quoted what Obata Sensei has written in his website. Probability theory has developed along the contemporary mathematics into stochastic analysis, while algebraic and combinatorial structures in probability are motivating problems in quantum non-commutative probability. He's interested in exploring the origin of stochasticity in the non-commutative nature. His study in principle driven by mathematical interest and is encouraged by communication with research. His research topics broadly are quantum probability, mathematical approaches to networks, and infinite dimensional stochastic analysis. And now to the end, the summary, I present you a fun fact that Obata Sensei birthday is August 17, coincident with Indonesian Independence Day. So Obata Sensei, your birthday is celebrated by the whole country in Indonesia. Okay, now without further ado, I invite Professor Nobuaki Obata to present your talk. The stage is yours. You have 60 minutes.
Okay, thank you very much for your kind introduction, and also it is my great pleasure to have this opportunity to give my talk today. And I've heard already the Combinatorics Today series is getting very important, and maybe will be a very important traditional event in ITB. And also, I am very honored to have your dean's Professor Wahyu's speech just before my talk, and it is my great pleasure to hear that. And okay, now I am going to start. So just a moment, please.
Yes.
A similar strange situation happening. So just a moment.
You go to share screen, green button. Yeah.
Yes.
Okay.
We can see your slide, Sensei. Oops. Off again.
Okay, now can you hear me?
Yes.
Yes, yes,
And
yes, we
also,
can see it.
can you see my slides?
Yeah.
Yes.
Yes,
Okay.
yes.
I'm sorry for this trouble.
Okay.
Something strange happened to in my computer. Okay, I'm sorry for the delay. Okay, today I'd like to discuss these topics and mainly quadratic embedding constant. That is a new idea that was introduced by myself maybe 4-5 years ago. So still I'm wondering it is really interesting or not. But anyway, I'd like to have your opinions or advice on this new concept. Okay, so first I'd like to give you definition of that new quantity. So I am working on the graph, and graph is a very common subject, but I am just, to be sure, I'm just saying a few conditions. My graph is mostly finite, but of course we can discuss infinite graph too. And graph is unoriented, simple, has no loops, and assumed to be connected. So for such a connected graph, we can introduce so-called graph distance. Namely, we can measure the distance between two vertices, which is defined to be the length of a shortest walk from X to Y. It is a very common subject. So once you collect all such graph distance, we can form a matrix, which is called distance matrix. So I denote it by capital D. And the entries of this matrix is denoted by small d xy, like this. And obviously, the diagonal entries are all 0. And this matrix is a symmetric matrix. And other entries takes value in positive integers. Okay, this distance matrix is my main target. Now I am going to define the quadratic embedding constant. So Z is a connected graph, finite or infinite, but in my talk, mostly finite graphs. And we consider the distance matrix. And once you are given a distance matrix, then we can consider the quadratic function of this type. If the number of the vertices is n, then f is n-dimensional vector. And we consider this quadratic function, and the quadratic embedding constant is defined to be the supremum of this quadratic function on the submanifold like this. If f is just a norm squared, therefore this means that f runs over on the unit sphere. In the second condition, this capital 1 stands for the vector of which all entry is 1. Therefore, this second condition means that the vector f is orthogonal to the vector, constant vector 1. So on this subset, this is actually a codimension 2 sphere, compact space, smooth one. Therefore, we can consider the maximum or supremum of this quadratic function on that sphere. This is the definition of QEC. This is just for your information that the inner product f and g is given by this formula, and the inner product of 1 and f is given by this. these formulas are valid also for infinite case, but we don't go into the infinite case today, so everything is finite dimension subject. Okay, so actually for a finite graph, this QEC is by definition taking the supremum of quadratic function, but you can replace supremum by maximum. Namely, there is exactly the vector f which attains the maximum value. Therefore, QEC is given by just the maximum. And another form of QEC is simple because we are considering the quadratic function like this, and this is bounded by some constant times f. This is norm squared. But if we are considering only f, which is orthogonal to constant vector 1, so we may find the smallest constant c satisfying this inequality. Then that c coincides with QEC. So this is a different form, but it's useful. Okay, so this is the definition of QEC, and this value probably is not discussed in the papers before I introduce this. Okay, so here are some backgrounds and motivations. So we are going back to a very old question by Schoenberg. This is a very old question. Suppose we are given a matrix K, Kij. This is n times n matrix. And then the question is to find points in P1 in Euclidean space Rd, points P1, P2 up to Pn, satisfying the following identity. Namely, every matrix entry is just a Euclidean distance square of points. Okay, so given a matrix K, then the problem is to find out points P1, Pn in Euclidean space such that the Euclidean distance square gives the matrix entry Kij. Okay. This question is divided into two steps, actually. First, conditions in terms of matrix elements. This is not always true, so we need some condition for existence of such points. And second is just a construction of points, how to find out points. And actually this question I mentioned here is just for n times n matrix, but infinite case is quite parallel. I don't go into discussion, but if you are interested in also in infinite case, there is some parallel discussion. And it is convenient to name such a matrix, namely a matrix D of this type. Namely, there exists a P1, Pn Euclidean points, and Euclidean distance square gives that matrix entry. Such a matrix is called sometimes Euclidean distance matrix. And this has a long history, and there are many works around here in literatures. Okay, then I give you some simple examples. So now we are interested in Euclidean distance matrix. So here are two examples. Suppose we are in the two-dimensional Euclidean plane, and there are 3 points. The distance is 1 between vertex 1 and 2 is 1, and 1 and 3 also 1. And then this is a right triangle, then the diagonal, namely the distance between 2 and 3 is square root of 2. This is just a triangle in the Euclidean plane. Okay, then corresponding to this situation, the distance matrix gives this. Remember that the Euclidean distance matrix always considering the Euclidean distance square as an entry. Then here, this is D, namely 1 square is 1, 1 square is 1, but the square root of 2 square 2. Therefore, this is the corresponding Euclidean distance matrix. Similarly, if you consider the 4 points in the Euclidean plane and sitting like this, and distance is between number 1 and number 2 is 1. Distance between number 1 and number 4, 2. Then the diagonal is the square root 5. Then corresponding Euclidean distance matrix is given by this. Okay, this is a simple example of Euclidean distance matrix. Okay, now obviously Euclidean distance matrix satisfies these conditions. Diagonals are all 0, and entries are non-positive, non-negative, and symmetric. So, for example, you can consider this D. This is symmetric, positive of diagonal entries and 0 diagonal. Then you are seeking the positions of 3 points. But of course, it is impossible because this matrix gives you there are 3 points in the Euclidean plane, and the distance between 1 and 2 is 1. 1 and 3 is 1. But here, 9 appears. It means that the distance between the number 2 and the number 3 vertices is 3. But we cannot set 3 points in the Euclidean plane such that the distance is 1, 1, 3. It's impossible. Therefore, D is not Euclidean distance matrix. Okay, so such kind of question was posed by Schoenberg, and also he solved this question in these years. So, which kind of matrix is a Euclidean distance matrix? The answer is given as follows. Actually, the following 3 conditions are equivalent. The number 1 is just a matrix D is a Euclidean distance matrix. Namely, entries are given by the Euclidean distance squares of 2 points. Sometimes we consider these PIs are map from index set I to Euclidean space. So this map is called quadratic embedding mapping. This is just a terminology. Okay, this is the definition of Euclidean distance matrix actually. Then this condition is equivalent to the following 2 conditions. The first condition is that this D is conditionally negative definite, C and D, where conditionally negative definite means that the quadratic function associated to this distance matrix D is non-positive for every f orthogonal to constant 1 vector. You remember, quadratic embedding constant is the maximum possible constant such that this quadratic function is bounded by constant times f norm square. Therefore, this inequality means that QEC of D is non-positive. Here appears this constant. And another condition is this. We consider the one vertex V in V, denoted by O. Then we consider the matrix A where the index are running over all V but O. Then we consider this matrix, this is by definition of Aij. then this matrix A is positive definite. This is the usual sense. Quadratic function associated to matrix A is non-negative for all F. So these three conditions are equivalent. This is a result of Schoenberg. And this is my starting point. Here appears QEC constant. So I can use QEC constant for this question. And here is a proof, but I omitted. This is just outline. Okay. Now I like to apply this idea to a graph. So now we have a graph, and the vertex set maybe we can arrange in a good way in the Euclidean space. Then I hope that the arrangement is good enough to have this identity, namely X and Y are vertices in the graph. This is the graph distance, namely the length of shortest walk from X to Y. Okay, this is graph distance. That graph distance is given by the Euclidean distance square. If you get such a good arrangement of the vertices, then we say this phi is quadratic embedding mapping. So applying the Schoenberg theorem, we know that this graph admits quadratic embedding if and only if the distance matrix is a Euclidean distance matrix. Then by Schoenberg theorem, D is conditionally negative definite. In our terminology, the quadratic embedding constant of G is non-positive. Thus, that old question is related to quadratic embedding constant. By the way, not a constant, but a quadratic embedding is also mentioned in some literature so far. For example, these papers. And the second book, number 2 is a book by Deza Roland. And this is a very nice book and contains many ideas around that. So I recommend you, if you are interested, I recommend you to see this book. Okay, up to here, if you are familiar with the spectral graph theory, then you are wondering the relation to distance spectra. It is quite natural idea to compare the distance spectra. Distance spectra is by definition the list of eigenvalues of the distance matrix. If the graph is on n vertices, then the distance matrix D is n by n symmetric matrix. Therefore, there are n eigenvalues. Probably some of them are identical, but we can arrange in the decreasing order like that. Then well-known Perron-Frobenius theorem, we see that lambda 1, the biggest eigenvalue of D, and the second largest eigenvalue lambda 2, there is a gap. Okay, therefore we have this decreasing sequence of eigenvalues of D. Now, our QE constant is just between lambda 1 and lambda 2. And actually, we have this identity. So QEC is strictly smaller than lambda 1. But compared to lambda 2, maybe equal, maybe not. So here are some interesting points. But anyway, for the moment, please see that our QE constant is loosely related to distance spectra, but QEC of D is not described by eigenvalues of D only. So it has some more information. That is maybe some interesting point, I believe. The proof is, for example, this is the first inequality is proven by using so-called Minimax Theorem. it is also known in linear algebra for symmetric matrix, how to compute the kth largest eigenvalue. There is a formula which looks like this. Then we consider the second largest. Therefore, we need to consider lambda 2. But then comparing to this formula and the definition of QEC, we conclude that lambda 2 is less than or equal QEC of G. It's not difficult. Actually, we only, the point is to employ this so-called Minimax Theorem. Another second inequality is shown by Perron-Forman theorem. So I mentioned this name. Okay. So here, please remember that our QE constant is given by the distance matrix, but it is loosely related to distance spectra, and we have a little bit more information which is not given by the distance spectra. So maybe I hope there is some role of QEC. Okay, now how to calculate QEC? I like to show some examples and so forth. By the way, I sent this PDF file to Eddie, so maybe if you are interested, please ask Eddie to have this copy. Okay, so starting with the graph, then many people understand the most basic graphs: complete graph, path graph, and cycle. So I start with that. First, the complete graph is QE class. It means that the QE constant is non-positive. Path graph, also QE class. It means that it admits a quadratic embedding in Euclidean space. Okay. In fact, these are observed by a direct observation of the Euclidean arrangement. Not necessary to compute QE constant, actually. In fact, here are two pictures. Here is a K4. Now, please look at this picture in three-dimensional Euclidean space. Okay, so K4 is sitting just like regular polyhedron. Then we can put 4 points in three-dimensional Euclidean space in such a way that Euclidean distance between 2 points are all 1. But that one exactly same as the graph distance. And 1 to the power square, 1 to the square, 1 square is 1, just 1. Therefore, this is quadratic embedding. Similarly, P4, this bold line gives you P4, and this is quadratic embedded in R3. Now, please consider this is in the R3 space. Now, for example, endpoints, okay, these endpoints, Euclidean distance is square root 3, okay? Suppose the length of one edge is 1, okay? This is the unit cube. Then the distance between endpoints is square root 3. But the square root 3 to the square is 3. That 3 is exactly same as the graph distance because 1, 2, 3. Okay. So this way we can embed P4 satisfying quadratic embedding. So in this way, of course, and if you consider the Kn or Pn, then you need to prepare higher dimensional Euclidean space, but similar. So These examples, these pictures show that Kn, Pn are both QE class. Therefore, QE constant is non-positive. Later, we are interested in the exact value of QE, but for the moment, we understand the codec embedding like this. And also, the cycle permits the codec embedding in Euclidean space. But actually, our proof by eigenvalues later. Okay, and this observation, this kind of argument was already done about, let's say, more than 10 years ago by these people. Now, now I'm going to mention the method of computing QEC. This is a quite elementary question because we are dealing with just a quadratic function and the maximum value of quadratic function under certain condition. Actually, there are two conditions. One condition is norm square of f is 1. And another condition is the inner product of 1 and f is equal to 0. Namely, f is orthogonal to the constant 1 vector. Therefore, the first equation gives you the codimension 1 sphere, unit sphere. Second condition is just a plane. Therefore, we know that unit sphere and considering the cross section with hyperplane, again sphere. Therefore, this question is very simple. The certain codec function, and we are interested in the maximum of certain codec function on that sphere. Therefore, we can apply Lagrange multipliers. So here is the target square codec function. And the condition, there are two conditions. Therefore, we need two parameters, lambda mu, and introducing such a function. And we are seeking for the stationary point of f, namely the derivative with respect to f. F is just a vector. There are n coordinates. Therefore, the derivative with respect to xi is 0. And also lambda derivative with respect to lambda and with respect to mu, all 0. So if you consider this equation and solving this equation, we get f lambda mu. So this is the stationary point of f. And we know that the maximum of this conditional maximum of this codec function is found among these points. Actually, our case is convenient. QEC is attained by some f lambda mu in this stationary point. That is a general theory. But if such a point, f lambda mu, is given, then the derivative of this function is 0. And actually, some small computation will get this identity. Namely, if f lambda mu is in the stationary point, then we have this identity. Then taking the inner product with f, then ff, inner product ff is 1. And inner product, oh, excuse me, this is not f, it is 1. I'm sorry. But the inner product is 1 and f is 0. Therefore, we get. So as a result, once you get the set of stationary points like this, then there appear several different lambdas there. But our QE constant is the maximum possible lambda among this stationary point. So that is our basic tool, how to compute the constant. So the story is simple because this is just a quadratic function, but the actual computation is not easy in some case. And there are some interesting questions, I think. But for complete graphs and related graphs, some are easy to compute. Actually, complete graphs, the QEC equal 1, complete bipartite graphs, also it is computable. And we have exact value of the QEC of complete bipartite graphs, KMN. And looking at this formula, the QEC non-positive if and only if m equal 1 or n equal 1. It means that the graph is just a star. Or m equal n equal 2. In this case, you see, this is just a cycle C4. Except such case, all QE constant positive. It means that complete bipartite graphs, for that case, for such parameters, are not embedded in Euclidean space. And another completely bipartite graph simple case, and you can compute. These are just examples. And I tried to obtain exact values for some special case. Complete graph deleted by some edges. Something like this. There are some formulas like this. And also, already 4 years ago or so, I started with collecting exact values of small graphs. So there is a simple list of connected graphs on vertex. 2 vertices, 3 vertices, 4 vertices. And if you look at this, mostly QE constant negative, but sometimes 0 appears. Okay, now we are coming to the 5 vertices case. And QE constant again mostly negative, but some appears sometimes 0. All right. And now new example appears, number 10. This is positive QE constant. Okay, positive. And again 0 appears. And actually there are how many? 21 connected graphs on 5 vertices. And among them, only 2 graphs have positive QE constant. Number 17 is the second one. Something like this. So this is just for reference. But if you are interested, please look at this paper. There is this table. And now here, I like to mention the distance spectra and QE constant again. So already I mentioned that the lambda 1 QE constant is between lambda 1 and lambda 2. And if the graph has the property called transmission regular, it means that the distance matrix has constant row sums. Namely, this is the condition. This is the row sum of the matrix, and this is independent of X. It is such a graph is called transmission regular. Then this transmission regular, the second largest eigenvalue is equal to QEC. So this is a case of the identity. But the proof is very simple. Actually, the constant one vector is the eigenvector of D. Therefore, the second largest eigenvalue is just considering the orthogonal complement of the constant one vector and so forth. So the observation is easy. So maybe some people are wondering, how about the converse? But unfortunately, the converse assumption is not true. I will discuss later. And for cycles, cycle is apparently transmission regular. Therefore, we can use this formula. Namely, we need to find out the second largest eigenvalue of D. Then that gives you the QE constant. But for cycles, the distance matrix D is so-called a circular matrix, and the computation of eigenvalues is easy. And we can have this answer. These QEC coincide with the second largest eigenvalue of D. So far, I show you some individual computation-based result. But it is necessary to consider a more systematic approach. So here I am rushing to show you something. First, a subgraph. If the graph G is embedded in other graph G tilde isometrically, then we have this identity. Isometrically means that the distance matrix has this form. Here, the bold line gives a small graph, and G tilde is a big one. So if you consider the distance between two vertices in this small graph, even in the G tilde, there is no shortcut. Then the distance matrix has this form. Then we have this inequality. And then apparently, if QEC of G tilde is non-positive, so is G. So this is first conclusion. And if QEC of G is positive, then so is G tilde. So we can use this inequality in such a way. And every graph G has a K2 as a subgraph embedded in isometrically, and the QEC of K2 is -1. Therefore, always QE constant is greater than or equal to -1. So this is a lower bound. And we try to derive some formulas for star product. Maybe in the graph theory, people call this operation in a different way, but I use this terminology following some other literature. So if you have two graphs and putting together at one vertex, then we have another graph. Then we are interested in QE constants. So we have this kind of inequality. So if you consider star product, then QE constant is greater than or equal the maximum of QE constant of the G1 or D2, and bounded by some constant. This constant is a little bit complicated, but we get this estimate. So as a corollary, if Q1, Q2 both are negative, then we can check that Q12 also negative. Therefore, we have this result. And if you take G1 to be complete graph, but a complete graph QEC is lowest possible QE values. Therefore, from this identity, we have this identity. Namely, if you have a graph G and we take star product with complete graph like this, then we have this identity. Actually, this is published quite recently. And there is one criteria to have strict inequality here. Namely, QEC of G is negative, this is assumption. And then there is a vector F attaining this QEC like this. Okay. And moreover, this is a touching point denoted by O. So this function F at O is not 0. Then we have this strict inequality. By using this inequality, we have observed that the QE constant of path is strictly increasing sequence like this. And second example is a kind of counterexample. If G is this graph, and we consider the star product with K2 like this, but in this case, the QE constant of G is attained by certain vector F, but FO is 0. In that case, we are wondering this is strict or equal, but it happened that it is equal. So some case, even you take a star product, the QE value doesn't change. It happens. So here is the question, namely, the converse of this theorem is true or not? This is an open question. And here another operation is direct product. Maybe the time is running for quickly, so I skip it. And also graph join. If you have two graphs, then there is an operation called graph join. In that case, also some result is obtained just for regular graphs. Unfortunately, general case, it looks a little bit complicated. So I am trying to do some examples. But for regular graphs, there is a good formula. So we can get some exact value of QEC. For example, wheels, complete split graphs, friendship graphs, and so forth. Okay, now we are coming to the last part. Actually, this is my main project for the moment. Now, I didn't mention anything about QE constant of path. Path graph admit a quadratic embedding in the Euclidean space, as I show you by pictures. Therefore, QE constant of Pn is non-positive. Then it is quite natural to ask, what is the exact value of QE constant of Pn? But it has not obtained. Actually, recently, the joint paper with Baskoro, and we proved that this sequence is strictly increasing, converging to -1/2. But finally, recently, my Polish colleague, Motkowski, obtained the exact value of Pn. So this is exact value of QE constant. The computation is somehow technical, and he used some determinant, some polynomials associated with certain determinant, and he checked the zeros of that polynomial and so forth. But anyway, now his paper can be found in the archive. Then if you are interested in this kind of computation, real argument, please refer to his paper. So finally, QE constant is obtained like that. Okay, then we are coming to interesting question. So I already mentioned that QE constant is between the largest eigenvalue of D and the second largest eigenvalue of D. QE constant is in between them. And if D is transmission regular, this identity holds. It's easy to see, but the converse is not true. Path graph gives a counterexample. For even n, second largest eigenvalue Pn is equal to QEC. But for odd n, we have strict inequality. Actually, in the 1990 paper by these people, second largest eigenvalue of Pn is obtained. There is not a very direct formula, but an implicit formula, but we can check it. So for even n, equality happens. For odd n, no. And obviously, Pn is not transmission regular. Pn is not symmetric, not very highly symmetric. Endpoint is somehow exceptional points. So we have this. Thus, problem one is to characterize the graphs G with this identity. I have no idea how to approach it, but it may be interesting. If you have some idea or some suggestions, I'm happy to hear that. Okay, second problem. This is actually my project now. We have a QE constant of path. It is strictly increasing, converging to -1/2. So they are plotted in this way. And 0 appears here. And over 0, there are non-QE graphs. Okay. So in the recent paper with Baskoro, I classify graphs only up to QECP4. First of all, QE constant is equal to 1 if and only if G is complete graph. There are no other type. And there is no graphs between -1 and -2/3. There is no graph. And QE constant -2/3, then graph is just P3, only path graph on 3 vertices. Something like this. And the next interval, we could characterize the graphs. Actually, it is a star product of Kn and K2, or K3, K3, or something like that. So in this way, I hope to have some systematic way of determining graphs between these intervals. And also, it is a related problem which may be interesting, is to characterize the graphs that the QE constant is less than -1/2. This is more realistic problem, I think. For each interval, maybe difficult, but up to -1/2, maybe there are some common structure here, and we can characterize such graphs. We hope so. And finally, non-QE class. Okay, you see, here is a scale of QE constant, and 0 appears, and over 0, this is a class of non-QE graphs. There are first 2 facts. All graphs on vertex less than 4 or equal vertices are all QE class. Namely, QE constant is always non-positive. There are 21 connected graphs on 5 vertices. I showed you the table, among which 2 graphs are of non-QE class. These are graphs, non-QE graphs. This is a complete bipartite graph, and this is this. Okay. Now look at this complete bipartite graphs. QE constant is exact value is known. And this is the answer. So QE constant non-positive if and only if m equal 1 or n equal 1 or m equal n equal 2. So first non-QE case is K32. The QEC is given by this number 2/5. And look at this general complete bipartite graph. Then we see that other m and n, of course, a QE constant is positive, but non-QE property is followed from that following inclusion, namely K32 is isometrically embedded in KMN. Therefore, we can say that general KMN is non-QE because it contains K32 isometrically. So I pose the following question. Find the primary non-QE graphs. Primary means non-QE graphs which don't contain any non-QE graphs as isometrically embedded subgraphs. Namely, okay, here you see KMN general case is not primary. It is non-QE but not primary because it contains non-QE graph K32 like this. But K32 doesn't contain any non-QE graph, subgraph. Therefore, this is primary. In that way, I hope to find the class of primary non-QE graphs. This is a quite open question. I am doing to collect some exact, explicit, small non-QE graphs for the moment. But I hope to have some systematic study for this question. Okay, thank you very much for your patience. So QE constant business has just started and very slowly developing. But I believe that QE constant is worthy for further study. And I welcome any comments and proposal. If you have any idea, question, or comment, I'm happy to hear that. Thank you very much for your patience. Thank you. That's all today.
Okay. Thank you so much, Obata Sensei, for a very stimulating talk. We give applause for Obata Sensei. Now, before we continue with the QA session, we will have a short break. Pak Edi, would you please?
Okay, so thanks again, Professor Obata. So now we will give all of you a performance, yeah, from what we call it Keluarga Paduan Angklung ITB. This is all. This song will be played by students, yeah, ITB students, with the instrument we call it angklung. So this is an orchestra of angklung, and they play some medley song, and this is a pop song, yeah. Is that right?
Maybe
Okay.
Obata Sensei, could you please turn off your shares?
Oh.
Okay.
Okay,
I'm sorry.
okay. Thank you. Yeah. Yeah, great. Okay. Let me open. Yeah, good. Okay. It's okay, the sound?
Yeah. Now the sound. A bit delay, Pak Edi? The sound is a bit delayed for me. Oh.
Sorry.
very impressed. Impressive.
Okay, very interesting performance, Sensei. Yeah.
Oh yeah. I know that instrument, music instrument, but in a smartphone, everybody has some part of the instrument.
I think so. I think so. Yeah.
How to play? How to?
Yeah. I don't know for sure, but I will ask if you remember Intan, our colleagues, she's the what you call the supervisor for the club. I will ask her how to. Okay. Okay. Now, sorry. Now it's time for Q&A session. I think it's already one question in the chat. It's quite long. I will invite Intan Sherlin. Could you please to ask directly to Obata Sensei?
Okay. Thank you very much, Yuda. Good afternoon, Obata Sensei.
Oh yeah. Okay. I'm reading that chat now. Okay.
Okay. Should I directly ask you the question, or
maybe you can ask this directly?
Yeah, please ask me.
Yeah, okay. First of all, I just want to say that it is a very interesting lecture that we have from you this afternoon, and it's such an honor for me to be able to learn directly from the person who actually invented the QEC himself, which is Obata Sensei. And as a in the doctoral program of ICB, I've actually learned the algebraic graph theory course on my first semester, and I found that this QEC topic could actually be taught on that course. So perhaps if Professor Eddie or want to invite you to be the guest lecturer somehow, it will be really nice to have you to about this in that course. And as in my question, I just can't help but wonder whether you have already involved some programming software to help you with the calculation of the QEC, or you just did it all by hand calculation. Thank you.
Okay. I'm sorry that that the connection is not very good, and but I could read your comment. And as for that, actually using some software or computer, it is very helpful. So far, I started this business about 4 or 5 years ago, and the development is very slow because I had not so enough time to concentrate on this project only. But so during that time, I hope to have some good computer software to compute QEC numerically or like a formal computation like Matematika anyway. But for small graphs, I computed by hand, basically, one by one. And so now I am interested in the case of vertex 6. There are more than 100 graphs. And the next one is 7. It's much more. As you know, and the number of graphs is growing very rapidly as the number of vertices goes to infinity. So the computation by hand is not realistic actually. So I hope to have some good computational software. So if you could develop something, then I'm very happy, and it's very nice to have such one. That is the situation. So my answer is, for the moment, I hoped, but not realized yet. Okay.
Thank you, Sensei.
Okay. Okay, thank you, Obata Sensei. there any other question? I haven't got any in the chat. If you want to ask question or give comment, please raise your hand.
But anyway, and if you are interested in this topic, and I left this PDF file to Eddie. I sent to Eddie just before my talk started. So
we already distributed to all the audience here.
Really?
Yes, by chat. Yeah, by chat. Yeah. Can I ask something, Bu Hilda?
Yes, please, Friday.
Yeah. Okay. So, Professor Obata, so you have very nice theorems about transmissions regular graph, right? So if you apply this, you end up with the QE of this graph is equal lambda 2, the second biggest lambda. I just wonder if we have vertex symmetry, for example, graph. So this vertex symmetry belong to transmission regular graph, right? Yeah, and also yeah, and also many kind of I mean classes of graph that can be in this class, yeah, in this transmission regular.
Well, how do you think many
is it
graphs?
Correct? Symmetric vertex symmetric graph is transmission regular graph or not?
Yeah, okay. And if the graph is highly symmetric in that in the sense that if you start at one vertex and look at the graph from that point, and the scenery is same, independent of the choice of your origin, and such a graph is certainly transmission regular, but it is quite highly symmetric.
Highly symmetric. Yeah.
For example, path graph is not at all.
Yes. But cycle is transmission regular, yeah. Yeah.
So and yeah. So the question is the gap between the class of transmission regular graph and the graphs with lambda 2 equal QEC. Yeah. There is a gap. So what is the gap? That is my question. But that I have no idea for the moment. Path graph gives you some class of between them. So.
Do you have an example that a graph that not transmission regular, but they have lambda 2 for the for the QEC?
Yes, there are some graphs I have, but and actually so far I am not so how to say spend the time in the distance spectra, rather QEC. But recently I found such a question. So also, but you know, and distance spectra has already some history in the literature. So there are some literature. So I am now studying it. So comparing their result and QEC business now. That is actually what I am doing now. So still slow, and I need your help.
No. We learn from you.
Yeah. Still, I'm wondering, it is a really interesting subject or not. That is, I have no guarantee. But I myself enjoy.
No, it's becoming interesting subject. Intan, the one who just asking a question, is one of my students, and she's interested to this topic as well. So I will ask her to to study this topic.
Then please let us do something together.
Okay. Great. Excellent.
Okay. Thank you, Pak Edi. Is there any other question or comments? Okay, I think we will end the QA session. And once again, we thank Professor Nobuaki Obata for sharing with us his current research, which is very motivating. Domo arigato gozaimasu.
Okay.
Thank
Okay.
you very
So
much.
thanks again
Now
to
I hand over
Professor
the program
Obata.
to Professor Eddie. Professor Baskoro.
Okay. So thanks again to Professor Obata for wonderful and inspiring talk. And we would like, on behalf of the Faculty of Mathematics, Natural Sciences, ITB, we would like to present you some appreciation here. Let me share with you. Okay. Okay, we will give you some certificates, Professor Obata Sensei.
Thank you very much.
So these certificates for keynote speaker of this program, and also we will send you these pictures.
Nice.
So this nice picture drawn by our students, of course, with the help of the computer. So this is dedicated to Professor Obata. Okay, so thanks again.
Oh, thank you very much. Very kind. Yeah. So
Okay.
today I enjoyed myself very much, and I feel home.
Great. You are our distinguished member
Yeah.
of our group. Okay.
Maybe you are already used to this kind of online conference and so, but I'm old person, so I like to see directly.
Okay.
Not on
Next.
the two-dimensional.
Yeah. So next May, you may come to Bandung
Yeah, I hope that
to
is
attend
the
the
problem.
conference.
Yeah. The difficulty is just the control of COVID.
Yeah.
So,
hopefully, the situation getting better and better. Yeah.
I hope so,
And we can
really.
travel easily. Yeah. Okay.
Yeah.
Hopefully. Yeah.
I hope to come ITV once again, and also
Great.
please come to Japan and Sendai.
Sure.
We are welcoming you always.
Okay. So thanks, Professor Obata.
Thank you.
And thank you to everybody here for attending this program. Okay. So terima kasih
Thank you,
banyak.
Prof. Obata.
Yeah.
Yeah.
Bye-bye.
Okay,
Professor
thank
Obata.
you, Obata Sensei.
Hi. Sayonara. Bye-bye.
Sayonara. Bye.
Sayonara.
Okay.
Okay.
I am getting out. Okay.
Yeah.
Okay.
I am getting out now.
Okay. Don't worry.
Yeah, okay. See you again.
Yes.
See you.
Bye-bye. Ya.
Bye.
Terima kasih semuanya ya. Oke.
Sayonara.
Terima kasih Bu Hilda, Bu Rino yang sudah main angklung.